Wow. Hello. Thank you very much for saying that I'm the best. And thank you for staying so late at the day. I'll try and be focused on this. So I'm Adam. I'm from Immersics. We do retinal eye tracking, which is a different way of doing eye tracking. I'll mainly try and focus a little less on what we do, maybe a little bit at the end. And I'll try more to try and understand where we stand today with eye tracking in general, use cases for eye tracking, how does that fit with everything else that we do. So I think that the maybe past year was interesting or significant for us because we suddenly see eye tracking everywhere in different devices. Of course, Vision Pro and other stuff. But we also see people do interesting things, not just us, trying to understand intent, trying to understand what people do besides just understanding where they look at, or use it for things more than we heard about in previous years. What we also see is that the classical eye tracking, the one that's been around for, I don't know, maybe more than a decade or maybe 15 years, has become more standardized. And you can even get it as open source. You can apply it yourself. You see it everywhere. And it's also decent for many things. I don't know, foveated rendering, basic training, testing. It works. So what we're here to talk about today, in brief, I hope, is what can you do more and why do you even need to do more than that, than what already works today and is out there today. So I think, like a classical slide, is that there's for eye tracking people, there's a fork in the road. What I just now said, classical eye tracking is being commoditized. You can do a lot with that. But at the same time, we're all trying to do more with the devices. As we, as eye tracking people, serve the devices that we're in, the XR devices. And the industry is now undergoing, let's call that, some sort of a rebirth, trying to offer more and be more exciting. That forces us to try and serve that. And that is in a very challenging environment because at the same time, the hardware people are trying to make the devices lighter and smaller and take less power. So, in simple terms, they're trying to make us do more with less. So I want to look a little deeper into what goes on. So I promised, and I'll try to look into specific use cases. There are videos here. The videos are not real videos because we at Immersics decided that it's best not to quote partners, competitors, or other companies, but they're all based on actual data, either data that we gathered or data of other technologies, apart from one or two cases where you will actually see real live footage. So So the first thing I want to show is something very popular. We all have seen this past years. It's, let's call that the technician use case. So there's the MR or AR use case that stands behind this is that you can empower someone to do more, achieve more, even though he is less experienced, by either directing him while he's doing his job as a technician with some remote person more experienced than he is, or AI possibly, and also at the same time understand what he's doing. So in that capacity, eye tracking is very instrumental. A classical case for that case that we've seen, I think, in AWE last year from Magic Leap is the networking case. Right? There's a technician. He's looking at a lot of wires, and he needs to put this in the right place. Somebody's telling him what to do. So my question to you, and you don't need to answer this, is which port is he looking at? That is more or less an average accuracy of classical eye tracking that we see today. There's an answer to this. You should be looking there. This is, by the way, all these videos show unfiltered eye tracking. The purple mark is after smoothing, after filtering. This is a classical example of accuracy level. The yellow square is a little less than half a degree at this field of view. So if you want to know in a situation like this where a person is focusing at, it's very hard given the technologies I mentioned before. Or in other words, that's a challenge we need to rise up to. Another scenario that people talk a lot about is assisted shopping. I go in a supermarket, there are a lot of products, I look at something, and I get more information. Nutritional facts, price of the same product in other places. But that requires us to understand exactly which product a person is looking at. And again, let's try and understand which product the person is looking at here. The problem of shopping is a little bit harder because unlike a technician who's focusing on something right in front of him, at the supermarket scenario, we browse through the shelves, right? And we are moving, and there's a lot of light, and the distances varies, so it's harder. And I froze this here, but in actuality, it's harder. And again, person here is looking at that tag. There are other cases where the current level of accuracy is a challenge. Like for instance, this is the actual tag on one of those products. Nobody's looking at the product like that. This is filling the full field of view. If somebody were to take whatever product and put this close to their eyes, they would probably not need any XR device, right? Or because they're seeing it. But even at this distance, you can see that a single line there is about, depending on the field of view and device, but in this case, it's a little more than 1 degree. But if you look at it in more realistic terms, then yeah, much less. So if I'm interested in, actually I can't even read the line, but if I'm interested in that line and I can't read it and I need someone to tell me what's written over there, we first need to know that I'm looking exactly at that. Here's a problem. Many of these use cases that I'm bringing here today are not necessarily innovative, new, or doing things we haven't heard about. They're simply things that everybody's talking about and we haven't achieved yet. One of these, for example, is the use case of enterprise Windows. I want to see a Windows computer in my VR, and I want to select the menus, but they're very small. I don't want to do a different UI like what Apple did with Vision Pro is amazing. But other companies feel sometimes that their employees are already used to this. They just want them to use the same thing. But in order to do this, they need to navigate. Just at the left side, you see a normal menu. That's already very challenging. The right-hand side is nearly impossible, right? And nobody wants to recreate that, especially for that. And the last one in this accuracy example is text. A lot of times we need to understand how people read text. But the letters are small. The words are small. So to understand on which word am I lingering? Did I read everything? Do I understand something? All of these are content parsing, text understanding, focused attention tests. There are different studies about this, but generally it's acceptable to say that a word is about half a degree, right? So that is a limit. I'm not saying, by the way, that eye tracking today cannot achieve half a degree. I'm saying that you need to achieve that level of accuracy all the time with everyone, which brings me to the next slide. The problem is we just seen at the rack example, the Raoul person. And he sees it like that. At the same time, with the same hardware, with the same eye tracking, at the same day, you take it off him and put it on Jane. It works way better. And then you take it off Jane and put it on David. It's horrible. So the problem is inconsistency across users with technologies that we have today. It's not just about accuracy, it's about if we are to, and we had a small conversation before this, if we are to manufacture devices that are consumer devices, they need to work very, very, very steadily across the entire population. But in reality, this is what happens today with eye tracking. It's a huge challenge. This is even worse when you're taking it out of scenarios like this, because if we go back to shopping world, maybe, yes. So usually people who go shopping and you need to help them assisted present more challenges for eye tracking. So the variancy grows. So chances are if you take any MR headset with eye tracking distributed to people shopping at Walmart, for instance, you'll have very big differences between the different people over there. So the question is why? Why is that the case? So with, I don't know, 15, 20 years since we started doing computer vision, with all the algorithms and the AI and neural networks and all knowledge that we have, how is it that it's still this inaccurate or inconsistent? And my friends from other eye tracking companies will forgive me now. It is not only up to how you analyze the data, which is all the technologies I mentioned, but also what are you looking at. So most, if not all, of the eye tracking methodologies that we see today look at the eye from the outside at some form or another. So either we're placing glints on the eye and we're looking for that, or we're looking for a feature like the pupil or the iris or something else. So we're looking at the eye from the outside, and the human eye is problematic. It's not a consistent organ, and it changes between people. And for instance, just one example, I can talk a lot about this, but just one example, if you're looking to identify the pupil, you're looking for something that is under a watery surface. So knowing exactly where it is at a, let's call that even a sub-degree level of accuracy, is a little bit like trying to catch a fish with your hand at a stream, right? There is a fraction. It's not exactly where you think it is. The eye moves. It's not perfectly round. Things move around. It changes along the day. It changes with age. It changes with different people. There are eyelashes, humidity. A lot of things affect the technology, and the result is that we need to adjust it. Some people call it calibration. Some people use other methodologies, like adding more sensors, or more LEDs, or more lights, or averaging between frames. All these are strategies designed to take the data that we get from looking at the eye from the outside and maximize the use that we can do with it. But we are paying a price when we do that. Remember that we said that we need to give more, but they are taking away the power and the weight. So if we add more sensors, more cameras, that's more weight. If we add more LEDs, that's more power and more weight. If we're averaging frames, then that's more latency. So there is a limit to how much accuracy and how much consistency you can get by looking at the eye from the outside. And unless you adopt some fundamentally different approach to do that, we are pretty much there. So that's the result we get. It's not that you cannot achieve half a degree accuracy, like I said earlier. The question is, can you do it over the same person consistently over time? So always half a degree or better. And can you do it over different people? So basically, all of these are looking at the eye there. So there is a lot of things at the outside of the eye. It doesn't really matter if you're looking at the pupil, iris, or something else. You're looking from the outside of the eye. But we know that when you're looking at me now, you're looking with your retina, right? You're not looking with the outside of the eye. Your outside of the eye is just a mechanism to bring the light to your CCD, to your retina. So what that means is that we need to extrapolate. After we theoretically, accurately identified where your pupil or iris or whatever other feature is Then we need to translate that to where your retina is. And that, like in any other calculation, has a degree of accuracy. Or in other words, that's another step that adds to the inconsistency. But what if you could actually track the retina directly? So then there are a number of advantages to that. This is what we do. This is how it looks from a sensor. When you track the retina, you're not looking at the outside of the eye. You're not subjected to any external features. From the inside, we all look the same. So it doesn't matter if you're 8 years old, if you're 80 years old, if you're European or Asian or something else, if you have small eyes or big eyes, if you can see the world, then it means the light goes into your retina. If light goes into your retina, then I can see it. Okay? So if I can see the retina, I can see something. That's one very important thing. The second thing is, this is my eye. This is my inverted left eye, I think. So you see there's a lot of nerves, blood vessels, and features there. That is lends itself very well to computer vision. There's a lot to track. Unlike the features I talked about earlier, this is objective. This is your retina for life. This is how it looks. If you look at it from 1 millimeter, 2 centimeters, or meter away, it would still look the same. So it's objective. Because it's objective, you can more easily extract an accurate gaze out of it very, very quickly. So with that in mind, we can achieve better results. Everything I'm showing here is achieved consistently. So it's not an average result. These are the results you get per frame. And so we talked about doing very, very intricate stuff. The day before I came here, I asked one of our beloved members who's sitting in the last row now to wear this system and take some challenging task. Okay? This is a system from the day before yesterday. So we are looking from, I don't know how far this is, maybe 12 feet, something like that, at a very small power outlet. And you can see that even when there are multiple power outlets, you can distinguish the one. This is unedited, this is the video as it is. With this, you can probably do more. Like for instance, actually I had the following video before I had this and I thought it's too tacky. So let's see both of them. So I thought, if you have 3 light switches and you can distinguish the one, then you can have interesting applications, right? Turn on the light, turn on the AC without getting up. This is the port that you need. This is the product that you need. That's the level of functionality that we think you can get with this strategy. That's it. Questions? We have our knowledgeable CTO here that can answer things that I maybe not privileged to answer. We also have a booth, 337, if you're interested in seeing the system working.
Hi, Josh Mason. So what is the limiting factor on 120 frames per second? Why all these very high...
No, there is no, okay, good question.
It said on your
Yeah, it did on the specification one. It's just a base measure for statistics. We support a range of frequencies, and for people who are interested exactly how the system works, we also have not only a different frequency sampling rates, but also varying one. So you can, using this technology, you can use a very high sampling rate when you're looking at something very demanding, like my light switch. And then you can go outside, have a watchdog, really lower it because you're walking to an area that is totally uninteresting, drop it to 10 frames per second. And then you're going into a shoe store, and we want to know if you're interested in a specific brand, and you can jump it back up. So that can really help in controlling power consumption.
I guess, oh, one more question. It looked like in the video that you showed that it was an external device. It was sitting on maybe the thing that was sitting on the table. Was that right? Or is it in a headset?
No, it's a headset.
I didn't know what was actually doing the tracking. No, back.
Oh, no, it's a phone.
Okay.
It's a meeting room with the.
So this is all done. This is all done in headset then.
Yes.
Are you currently deployed in any headsets?
No.
Are you working with any OEMs to bundle this as a solution? Is it an add-on for other headsets? How can people acquire this?
Okay, so I don't know, 4 questions there. No, it's okay. This is we are not okay. This is a technology that goes into, like any other eye tracking, into a manufacturer device. They work with manufacturers to embed this solution in their products. We currently have evaluation kits going out in a number of projects with a number of companies. Can't name any names. The way these things work for eye tracking solutions generally, or at least for this, is that the deployment is specific for the system that it's embedded in, right? So if one vendor needs it at a certain refresh rate, and also I didn't mention, so I wasn't talking about us as much, is that it's available at a single or dual cameras per eye. So that also means different positions of the sensors, different calibration options. So all that is a project that we do with each vendor depending on the use case.
Excuse my reach. Excuse my ignorance. So we use AR to deliver work instructions, and one of the limitations we have right now is anchoring the AR experience to be, accurate. Maybe I need to install something with high precision. Does the ability to have more like reliable or accurate eye tracking, can you compensate for
accurate anchoring of virtual content to the real world is more about 3D or spatial sensors than eye tracking.
Yeah.
Accurate eye tracking, especially accurate and low latency eye tracking, can help you when you move around. So let's assume that you have an amazing 3D sensing technology, like my friends from Voxel Sensors here. That can tell you exactly where the table is, what its height, what's your distance from it, and you place this virtual hand on it, right? As long as you're stationary, everything is good. But if you move, your perspective changes, right? And you need to adjust the content to that. So accurate and low latency eye tracking helps there. But it's both. They need to work together.
Any other questions?
Someone in the back.
Hi there. I would assume that you would need to map somebody's retina in order for this kind of system to work, like know what part of an individual's retina the camera is looking at. Is that correct? And if that is, what is the duration of the setup time for an individual?
Yes, 30 seconds. So yes, we need to map it's like facial recognition. You map an object, and then in the future you compare yourself to it. The advantage is that you need to do it only once per life per person, because our retina is pretty set from when we are 8 years old till we're 80, and start to deteriorate. It depends on the person. Currently, it takes about 30 seconds, 40 seconds to do it, a one-time process. And so yes, and 30, 40 seconds.
Time for one last question.
There.
Thank you. Andrei Volkov from True Life Optics. Is your system sensitive to glasses slippage and things like eye relief? Sort of how repeatable it is if I take my head-mounted display off and then put it on, maybe like
Okay.
slippage, what's it called?
No, so those are actually 3 questions. I'll divide them with your permission. Slippage is when the frame that has sensors move in relative to my eye, right? Taking off and putting back again is more of a calibration question for most companies, and eye relief is a third question. So it is for a, as long as we see the pupil, it is not sensitive to slippage. That's the answer to number 1. Think about this. This is like a really, really high-level example. If I take my phone out of my pocket and I try to unlock it with my face, it doesn't really matter if I do it from here or do it from there, right? It's the same concept. The second one, the big advantage is you can take it off. You can come back after 15 years and put it back on, it will work. Eye relief. We generally favor low eye relief. We like to be closer there because we need to look at the retina. So about 12 millimeters.
All right. Let's have a round of applause.
Thank you.